Okay, hello and welcome. And in today's video, what we're going to do is we're going to derive the sampling distribution of the sample variance. So, if you want to do point estimates, interval estimates, stuff like that, you need to know what the distribution is going to be. So, first of all, let's go and have a look and write down what we're going to try and prove, and then we'll go through the proof step by step. So, what are we trying to prove? Well, if we've got y1, y2, y3, comma, dot, 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 up to yn, and these are all distributed IID. What does IID mean? Identical and independently distributed with a distribution that is normal, a mean of mu, and a variance of sigma squared. Then if we take the sample variance, we times it by n minus 1 and we divide it by sigma squared. This thing has a chi-squared distribution with n minus 1 degrees of freedom. So now we could do things like confidence intervals, which we'll get to later. Confidence intervals for the sample variance. So sometimes you can run over this and not notice stuff. But first of all, I want you to notice how many observations we have. N. They all have the same, they're all normally distributed. They have all the same mean and all the same variance. So that's the things you might not have noticed there. So we're going to need for this, we're going to need a lemma. And what is a lemma? It's basically a proof that we're going to assume and use later. So in this case, we've got y1, y2, dot, 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 yn are IID. Normal, mu, sigma squared. So the same as before. But if this is the case, the sample mean, which I'll denote by y bar, and the sample variance, s squared, are independent. So you can see my bad handwriting. If we're lucky, Apple will make that slightly better. So let's think about the proof. Right. We're going to start a bit strange. We're going to start considering something that will look like, well, why are you doing that? But it will slowly come together. So I'm going to start and say, let's look at the sum as I goes from 1 to n of yi minus mu squared. Right. What I want to do is I'm going to end up writing this. I'm going to manipulate this into something I know, but it's going to be equal to two terms, which I'm also going to manipulate into something I know, and then rearrange it. We're going to end up with that n minus 1 s squared over sigma squared. So you're going to have to sort of, displace your disillusionment and say, what's happening here? Give me a chance. It will come together at the end. Well, the first thing I'm going to do, I'm going to write this as a summation. I equals 1 to n, yi minus the sample mean plus the sample mean minus mu squared. Now, this is a common trick that we use a lot in statistics, and at some point in one of the forms, we're going to have a look at statistical tricks. All I've done there is I've added 0. Because if I add the sample mean and take it off, I've just added 0. I haven't really changed it. But what I'm going to do is I've got a squared term here. I'm going to treat this as a and this as b. And remember, if I had a plus b squared, that would be a squared plus 2ab plus b squared. So I'm going to do exactly the same thing with this term. I'm going to have the sum as I goes from 1 to n, yi minus y bar squared, plus I'm going to have 2, the summation as I goes from 1 to n, yi minus y bar, times by y bar minus mu, and final term plus summation as I goes from 1 to n, y, let me just check my notes so I don't get this wrong, y bar minus mu squared. Okay. I said I'd have two terms on there. What I want to do, and this is a common thing, is I've got this cross product. I've got this thing here. I would really like to make that disappear. So let me show you that that's the case. We're going to have a little aside. And we're going to say, let's just look at that term. Well, we've got 2. The summation as I goes from 1 to n. yi minus y bar minus mu. Okay. First thing to notice is you look at this and go, well, what things have an I in it? Well, this has an I in it, so it has to stay there. But this whole term isn't, so it can come out the front. So this equals 2 y bar minus mu. The summation as I goes from 1 to n, yi minus y bar. Now, this summation is always 0, but let me show you why. So if we just take this bit here, this is the same as I equals 1 to n, yi, minus the summation n, I equals 1 of y bar. Well, if I added up all my observations and divided by n minus 1, I get the sample mean. So if I just add them up, this is equivalent to n times the sample mean. The term on the next term, I'm adding up n lots of the sample mean. So this is n lots of the sample mean. So this equals 0. So basically what we've done, we'll go right back here, we've shown that this is 0. So I can write this term as the sum of these two terms. So let's summarize where we're up to at this point, and I will go to my next little bit of paper so I keep up to date. So we've got the summation as I goes from 1 to n, yi minus mu squared. And I've now shown that this is equal to the summation as I goes from 1 to n, yi minus y bar squared plus the summation as I goes from 1 to n, y bar minus mu squared. Now, I'm going to divide everything by sigma squared. Now, for those who are worried, we're going to assume that sigma is greater than 0. So sigma squared is greater than 0, so I can divide all the way through without causing some sort of problems. We're now going to do some rearrangement. The first term here, I'm going to write this summation as I goes from 1 to n as yi minus mu over sigma all squared. Cool. The next one, well, I'm taking each observation, taking off the sample mean and squaring it. If I divided that by n minus 1, I'd have the sample variance. So this is going to be n minus 1, the sample variance, over sigma squared. The final term here, these are all constant. The y bar and the mu are all constant, so I've got n lots of y minus mu squared sigma squared. In fact, I'm going to make this term even better. I'm going to write it as y bar minus mu over sigma over the square root of n all squared. Okay. So let's think about what we've got. We've got a term over here, and we actually know what the distribution of this is. The yi are normal. I'm taking off the mean divided by sigma. That is a standard normal, and I'm squaring them. A standard number squared is a chi-squared, and I'm adding up a load of independent ones. So this is going to have a distribution that is chi-squared n. This is the distribution we'd like. We don't know yet. What about this one? Well, this is the sample mean minus its mean divided by its standard error, all squared. That is a chi-squared of 1 degree of freedom. Okay, so it's nice. The other thing I want you to notice is that the term here, this one, involves s squared, and this term involves the mean, but not both. And we know that s squared and the mean are independent. So function of these are all independent. So this term and this term are independent. Brilliant. You should know that if I want to get the moment generating function of this, of the sum of two independents, I can do it by the product. So if we say the moment generating function of this term is going to be the moment generating function of this term here, we don't know the distribution yet, we're having a good go, plus times by the moment generating of this one. Well, this one is a chi-squared on n, so we get that. Well, first of all, I can rearrange that to say the moment generating function of what we care about is the moment generating function of a chi-squared with n degrees of freedom divided by the moment generating function of a chi-squared with 1 degree of freedom. Substitute what that is. That's 1 minus 2 to the t minus n on 2 over 1 minus 2 to the t to the minus a half, which is 1 minus 2 to the t minus n minus 1 on 2. Moment generating functions are like signatures. Like if you can find the distribution of something and it's a moment generating function that you recognize, you know its distribution. So we've done all this arrangement, and what we've got is eventually we've said this thing here, this random variable, I don't know what distribution it has, but I know its moment generating function. What's its moment generating function? It's this, and we recognize this. This is the moment generating function of a chi-squared with n minus 1 degrees of freedom. So that's it. It's a little bit convoluted, you know. We had to start with a lemma because we're going to use the fact that these things are independent because we're going to need to be able to get the moment generating function. We started in a strange place, but eventually it all came through. So there you are. Nice little distribution or sampling distribution of the sample variance. Excellent. See you next time.